Hi, my name is Eileen Chu, and I'm now presenting my final presentation. The topic for my final project is accelerating radiotherapy quality assurance for cancer treatment plans. So the core idea for my project is a knowledge-based planning. In the dataset, I have around 1,000 patients, each with DICOM file that includes their tumor and body structures, plus the corresponding 3D radiation dose. So when a new patient comes in, the goal for my project is to check whether their treatment plans looks safe and reasonable. To do this, I need to search a large historical database to find similar past patients, mainly focus on their tumor-related features. You can think of this as a recommendation system. It's recommending what those patterns are safe for patients with similar tumors. So for the retrieved historical twins, we will compute the DVH, which is also called the dose volume histogram. It is a statistical summarization that shows what volume of organ received at least that dose. Uh, We'll then compare the cured patient's DVH against the distribution of the DVH from the similar ones. Based on how far the cured DVH deviate from the historical range, we will assign three kinds of flags. The green flags means it looks normal, and the yellow one means it needs caution, and the red one is the potential warning that deserves a closer look by the radiologist. Just for explanation, you can see two example DVH plots at the bottom of the slides. These are for two different organs for the patient. So in both plots, the red line is the cured patient, and the other curves shows a similar historical twins. On the left plot, you can see that the red line is well outside the cluster of the historical DVH. This means that the current plan is delivering much higher dose than what we usually see of similar patients. So in this case, this should be flagged as a warning and should catch the radiologist's attention. And on the right side, the red line stays within the green zone, inside the typical range of the historical twins. In this situation, the dose looks consistent with the past safe plans, so this organ should be flagged as normal. And for the current workflow, in the original implementation, these are three steps. The first one is to do the query and retrieve from the historical data set, and we will do the validation part. Um, After observing all the process, we found out that the slowest part is in the validation step. So for each test patient, after we find its historical twins from the retrieval phase, we will still have to load the full 3D dose and structural grids for each twin and recompute the organ level DVHs and compare them with the cured patient DVH to assign the normal or caution or warning flags. Doing this IO heavy and DVH intensive work, one patient at a time across thousands of patients is extremely slow on a single core. That's why I want to parallelize this validation workflow in this final project. So multiple patients can be processed at once and the whole cluster is actually used. After identifying the validation phase is our bottleneck, the first and most impactful step was changing the execution model from serial to parallel. These are some strategies I use to optimize the project. I will like talk about them in four steps. So originally, the code functioned as a simple Python for loop. It would take a patient, calculate the similarities, load the file, compare compute the DVA result, and only then it could move to the next patient. But in a very high performance cluster, this is a waste of resources. Even though we have maybe 20 cores available, the script would only use one. So to solve this problem, I found out that each patient can be processed independently in computing their DBHs. So it is very suitable for the data parallelism. So I implement this using Python's processing model. I treat this processing of each patient as an independent task, and instead of doing the loop, I instantiate the process pool. The main process acts as a distributor, splitting the list of patients and assigning them to work processes. And because they are separate processes, they each have their own Python interpreter and memory space. And this allows us to utilize 100% of the CPU capacity on a node. And it also serves as the foundation for all further optimizations. After parallelizing the data, the next challenge I had was about the memory usage. In Python's default multiprocessing model, when you pass a large training matrix to a worker, it gets pickled or copied. So if you have multiple workers, you can end up with multiple full copies of the extreme PCA in RAM, for example. So on a shared cluster node, this quickly become a memory bottleneck that can even cause the jobs to fail. So to fix this problem, I switched to the NumPy memory mapping. In the main process, I saved the extreme PCA to disk. And then inside each worker, I loaded with NumPy load function. This tells the operating system to memory map the file in read-only mode. The operating system handles paging behind the scenes, and all workers share the same physical memory pages instead of keeping their own copies. As a result, our memory usage stays almost flat as we add more workers, and the previous memory bottleneck is effectively removed. So we have parallelized the code about the data and the memory, but I also noticed another inefficiency step, which is about the communication overhead. Mm, so even though the data is on the disk, we still need to tell the worker where it is. In a naive implementation, we pass all file paths and configuration settings to the worker along with every single patient task. We had 1,000 patients and transmitting and unpacking these configurations 1,000 times. We are also asking the operating system to open files handles 1,000 times. This created unnecessary traffic between the main process and the workers. So to fix this problem and even to speed up the process further, implemented the worker initialization pattern. I used the initializer argument in a multi-processing pool. This runs a setup function exactly once when the worker process first starts up. Inside the function, I open the memory mapping handles and set a directory path into global variables. The benefit of this strategy is massive for high throughput tasks. So now when I assign a patient to a worker, I don't send a very heavy configuration object. I just send a tiny patient ID. The worker grabs the heavy data from its own preloaded memory. This minimizes the IPC overhead and let the CPU only focus on the mass. The last strategy for the parallelization uh, is uh, is to optimize how the tasks are scheduled on the cluster. So in the medical physics, tests are highly heterogeneous. So one patient might have 1 second to process, while other might, with a very complex autonomy, might take around 10 minutes. So if we split the list evenly, the entire job wait for one worker start with the difficult patient, while other CPU will be set idly. So to solve this problem, I made a pipeline environment awareness. So firstly, the code check the Slurm environment variable to dynamically set the worker count to match exactly what the scheduler allocated. And secondly, instead of assigning tasks sequentially, I used the IMAP and ordered with a calculated chunk size. The benefit for this parallel strategy maximize the throughput and achieve dynamic load balancing and predictability. So the next section is to show some results. Before we jump into the actual performance data, it is important to establish a baseline for success. To do this, I used Amdahl's law to calculate the theoretical maximum speed up we could expect our, for example, 8-core test node. So the prediction is plugging these numbers into equation with 8 cores. So if 80% of the code is parallel, the math predicts around like 3 times of the speed up. So a result within 3 times to 5 times range would indicate a very highly successful implementation. On this slide, I'm showing the actual wall clock speedup measured on Quest. On the left is the sequential version. I ran it in a single core with 32 gigabyte of RAM. Processing just 5 patient took around 3,696 seconds, which is a little over than 1 hour. And on the right side is a parallel version, and I used 8 CPU per task. The same 5 patient now finish around 1,000 seconds, which is around 18 minutes. That's roughly a 3.4 times speed up on real data, which falls nicely inside the 3 times to 5 times range predicted by Amdahl's law for 8-core node. So for this task, I only use 5 patient to keep the range manageable. But for the full pipeline, it needs to process about 20 patient against 80 reference cases. So from this number we tested, the sequential version would take on the order of tens of hours, whereas the parallel version brings that down to around half of a day, which is a very great output. And that's all for my final presentation and for my project. Thank you.